Today's lecture, we will discuss about microsensors and microtransducers. This is a part of module 4 in the course from microrobotics. As far as the module content is concerned, the objective of this module is segregated into 6 sub-modules, like fundamentals of, first we will be discussing about the fundamentals of microsensors and microtransducers. Then there is a more emphasis on optomechatronic system design, basically on optical based displacement sensors, sensors based on light intensity modulations, interferometers which are being efficiently used for microsensing related applications, and then we will also discuss about optical fiber sensors. Now, when we try to talk about this microsensors and microtransducers, these microsensors are miniaturized sensors that detects physical, chemical or biological signal at a micro or nanoscale. They convert these signals into electrical output for further processing. So, in the other words, a microtransducer is a device that converts one form of energy into another at a microscale. It plays a crucial role in microsensor by transforming the detected signal in the form of a readable output. So, the small size, high accuracy and sensitivity allows them to be integrated into a compact electronic system where a minor physical and chemical or biological change is getting converted into a measurable signal. So, ideally in the case of a microsensor, if we consider this as a microsensor, it has two different components. One is the sensing element and the other one is the transduction element. The sensing element will be in touch with the parameter and then it sends the impact which happens or the influence which happens on these parameters. Appropriately, the signal is fed into the transduction element. So, the main function of the transduction is to convert one form of energy into another form, so that we can analyze or we can sense can get the signal data about the parameter what we are trying to measure. Now, let us discuss about the history of this microsensor development. In 1960s, the first effort at adapting a microfabrication technique to the creation of the miniature silicon sensors. After temperature and pressure sensors, optical detector arrays were probably the first such device to find the way into production. And today, these devices are among the largest chips fabricated by the semiconductor industry. Hence, an earlier research in microsensors started with miniaturization of mechanical and electrical component using semiconductor fabrication techniques such as photolithography, thin film deposition and etching. So, if you see in this particular sensor, this is a structure and top view of a monolithic mass flow sensor containing transducer for gas flow rate. It is a direct type and pressure, and it can measure the pressure and the temperature. So, in this particular case, so we have a thermal based sensor which is integrated, a pressure sensor which is integrated, as well as a temperature sensor which is integrated. So, all these sensors are well integrated into in a single packaging system, so that appropriately this becomes a kind of a single unit for appropriate applications or appropriate functional devices. Now, in this particular talk, so we will be discussing about the concept of sensing element. What are the different types of sensing element which exist with reference to microrobotic application? How the sensing element has an impact with reference to different functional behavior. Now, when we try to look into the closer view of these microsensors, so microsensors are a part of wider class of micromechanical system device. Typically, the microsensor range from 10 micron to 5 mm. So, the defining the feature of any MEMS device is an element with some sort of mechanical function integrated with microelectronics. So, these microsensors can be generated as a miniature transducer, since they convert energy in the form of a measured mechanical signal into energy in the electrical form. Therefore, MEMS based microsensors have significantly evolved in terms of accuracy, miniaturization and power efficiency. Now, let us take an early example of a MEMS device. It is the resonant gate transistor, an adaptation of the MOSFET developed by a Robert A. Wickstrom in 1965. Now, the reason for bringing this particular example is, in a small scale, we find a mechanical system. We can observe an electrical system which is being integrated over here. So, any kind of complex systems can be connected appropriately in such a way that we can integrate this system for developing a kind of a micro devices or a micro robots based on the application. So, in this particular case, a force plate, it's a kind of a cantilever which is being established. The overall characteristics of the cantilever is sensed using a kind of a source diffusion using a bias voltage which is available over here. Now, as far as the main particular aspect of microsensing perspective point of view is the sensing element and the transduction element. In this particular case, let us consider this as a simple system. So, in this system, there is a kind of a resistor which is used and then there is a thermocouple which is available. Now, when a heat is made to incident on a thermocouple, the thermocouple appropriately converts into a current. So, this is what is a Seebeck effect. Now, in this particular case, the heat which is getting generated and the thermocouple which is directly used for sensing is considered as a sensing element. The conversion of this heat into an appropriate voltage or potential difference, which we call it as a transduction element. Let us take the example of the second case. So, in this particular case, it is a MEMS silicon resonant pressure sensor. So, in this MEMS silicon resonant pressure sensor, we have a diaphragm in place and then there is a pressure which is exerted into it and the pressure is connected to the resistance R and then the current I over here. So, what happens is when the pressure is incident on it, this diaphragm will try to move back and forth. From the movement of the diaphragm, so we can see a change in the resistance. So, ideally here the diaphragm acts as a kind of a sensing element and the conversion of this diaphragm, the pressure induced on this diaphragm to an appropriate signal which we call it as a transduction element. Let us take an example of this third system where it is called a self stiffness sensor using an ultra thin glass sheet, where there is a kind of cantilever which exists and then there is a pressure which is exerted on it. So, when we try to induce a pressure, there is going to be a deflection and the deflection is being measured using a kind of a transduction element which is available over here. So, the pressure is measured using a kind of a cantilever and the change in the pressure is measured with the help of this transduction element. Now, when we see the overall working of these microsensors, let us take a simple example. See, this microsensors which operates on the fundamental principle of converting a physical change or stimulus into an electrical signal, facilitating and detection and measurement of specific parameters in the miniaturized form. These sensors are crucial components in various fields due to their ability to detect and respond to changes in their environment at a macroscopic scale. If we try to see the overall components which are aligned in a microsensors, one is the sensing element as I had discussed earlier, then there is a coupling, a circuitry which takes care of the complete signal conditioning, etc., and finally a kind of a contacts which is being established, which is mainly meant for some kind of power distribution, etc. So, this is a kind of a skeletal structure of a microsensor, or I would say that this is a kind of a template which is used basically for microsensor fabrication. Now, when we try to narrow down our microsensors for robotic application perspective point of view, in particular for micro robotic applications, they can be considered under 5 main categories. One is a radiation based microsensors, a thermal microsensors, magnetic microsensors, mechanical microsensors and chemical microsensors. Let us go one by one about the different types of microsensors and the usage and application and design of these microsensors for different functional characteristics. Now, let us discuss about the radiation microsensor. These radiation microsensors are used to detect radiation with different energies or wavelengths such as X-rays, gamma rays, ultraviolet radiations and infrared radiations. Example, a photoconductive microsensor. So, this figure basically explains the principle of operation of a photoconductive microsensor, which depends on creating a conduction process as a result of the energy gained by the electron from the incident radiation. Specially, such microsensors depends on inducing voltage across a semiconductor junction when subjected to the radiation. So, these types of microsensors has an output resistance in the range of 100 ohm to 1 mega ohm. Now, when we try to talk about the thermal microsensor, the thermal microsensors are used to sense the thermal quantities such as temperature, heat flow and the thermal conductivity. So, we all are aware about it. When we try to talk about thermocouple, so thermocouple works on the principle of the Seebeck effect. Like in this, as far as the Seebeck effect is concerned, they use two different junctions. So, one is called as a hot junction and another one is called as a cold junction. The difference between, so because of this hot junction and cold junction, a kind of potential difference which exhibits over here. So, let us take an example where a platinum resistive temperature microsensor that depends on measuring the temperature by determining the change in the material resistance. They have a linear dependency of temperature, and as far as this microthermocouple microsensors are concerned, they depend on the Seebeck effect. They use materials that have different thermoelectric power. Here in this particular figure, it shows the basic configuration of a microthermocouple sensor where there are two metal junctions are kept, and then there is a reference junction is there and then the sensing junction is there. So, from the reference junction, so how much is the deviation which is observed is being sensed by the sensing junction. So, that is how the thermal microsensors can be easily integrated in the system. Now, let us talk about the magnetic microsensor. So, these magnetic microsensors are used to detect and measure the magnetic flux density. So, for example, we might have heard about this term called magnetogalvanic. So, these magnetogalvanic microsensor that depends upon the magnetogalvanic effect in which a voltage is induced across the slab of a material that is proportional to the applied magnetic flux density in a perpendicular direction to a current passing through the slab. So, here if you observe, this is a kind of a Hall effect microsensor. So, in this Hall effect microsensor, so what happens is, so we are trying to apply a high voltage over here. So, with reference to the magnetic field, with reference to the change in the magnetic field, the deflections are sensed. Another example of using a magnetic microsensor is called as a magnetoresistive microsensor. This magnetoresistive microsensor depends on the proportional variation of the material resistance with the applied magnetic flux density. So, in fact, with reference to magnetostructive effect, we have discussed a lot in the magnetostructive based actuator. Almost it is a kind of a same principle which is used for sensing related applications. Now, let us talk about a mechanical microsensor. So, on a larger scale, these systems are called as hot wire anemometers. So, these systems, they are considered to be most important type of microsensor due to their wider range of application and variety in their mechanical measurement such as flow rate, pressure, acceleration and force. So, let us take the example of these microsensors. So, these microsensors, flow microsensors are used to measure the flow rate of a gas or a liquid. They depend on the monitoring the heat transferred per unit time from a resistive wire heater to a moving liquid at 2 points via a microthermocouple temperature sensor as shown over here. Now, in other words, we can also represent it like this. Let us consider a coil. So through this coil, a flow is passing through it. This is connected to an electrical biasing. There is a voltmeter available over here. So what happens is, when there is a current is passing through this coil, and when there is a continuous convection of air which passes through this, so there is going to be a reduction in the heat. This reduction in the heat will try to draw more amount of current from the potential difference region, from the source. So from the amount of power which is drawn, we can estimate how much is the flow which is passing through it and how much is the temperature reduction which happens into it. This particular process is called as a hot wire anemometer. So it is mainly meant for flow measurement, temperature measurement, etc. Okay, so almost this also works on a similar concept. Only thing is, we are trying to scale it down at a lower scale so that it takes care of the flow direction. Now we have the chemical microsensors. As far as these chemical microsensors are concerned, they are composed mainly of chemically sensitive materials and a transducer. So a physical change occurs in the sensitive layer in the while detecting a molecule of the sample gas. This change is detected and converted by the transducer to an electrical signal. Example, conductimetric microsensor that depends on changing the electrical resistance of material when subjected to the target gas. This change is measured using a special device, and a Taguchi type tin oxide gas microsensor and the silicon microemission resistive gas microsensor are example of such devices. So if we try to observe in this, so there is a kind of a diaphragm and the silicon gas microsensors are available over here. So this active element is a kind of a diaphragm which will try to absorb, which is highly chemically sensitive, and it will try to disperse the amount of heat which is liberated. So these type of microsensors have a thermal operating range from ambient temperature up to 500 degrees Celsius. So this is a kind of a silicon based gas microsensor. Now when we are trying to establish these microsensors or microtransducers appropriately, there is a need to identify the material based on the requirement. Now when we try to look into the materials, so the materials which are commonly used for microsensors are silicon, which is considered to be a standard substrate material for IC fabrication, and thus the most common substrate material in microfabrication. So the use of the silicon substrate material enables the configuration of transducer and circuitry, example in CMOS based microsystems. So a single crystal silicon has an excellent mechanical property which enable the design of these mechanical structures. When we try to talk about glasses, these glasses exhibit attractive dielectric and optical properties. Several micromachining techniques such as isotropic wet etching and anisotropic dry etching have been developed to structure glasses. Now when we try to talk about ceramics, ceramics have been extensively used as a substrate for hybrid microelectronics and are common in microelectronic packaging. So the standard material is alumina and other materials like BO and ALN are efficiently used. Apart from that, we also have polymers. So polymers have been more and more explored as an inexpensive substrate material. So like a special process such as hot embossing, injection molding, laser machining or stereolithography has been developed to structure the polymer even in the micrometer range. Now let us see some of the key applications of these microsensors in micro-robotic applications. So one is a kind of a precision manipulation. So like for instance, when we try to hold a particular component, okay, so especially in the case of micro-robotic related applications where we are talking about a micro manipulation, so such kind of microsensors are efficiently integrated with the micro grippers so that the force is sensed and appropriately the inputs are provided to the system. So these microsensors are integrated into robotic gripper can measure the force applied to an object, allowing for a delicate handling of fragile item like surgical instruments or electronic components. Similarly, when we try to talk about the obstacle detection and obstacle avoidance, basically in the case of AGVs or in the case of small micro robots or a swarm of micro robots or micro drones, etc., a tiny proximity sensor can detect the obstacles very close to the robot, enabling the navigation in tight space and preventing collision with unexpected objects. Similarly, when we try to talk about the environmental monitoring, microsensors can measure temperature, humidity, pressure and air quality in a robot surrounding, allowing for an adaptive behavior based on environmental conditions. So, ideally you can integrate these microsensors with a drone or with a micro drone. We have also discussed about when we are discussing about the microelectronics, micro robotics, it was observed that micro robotics can be used for sensing the pollutant in the underwater condition, etc. In those underwater conditions, when we try to integrate these kinds of microsensors, especially the environmental monitoring microsensors along with the systems, so it can be used for sensing the pollutant individually. Okay, and then based on the type of the pollutant appropriately we can sense. Next is a kind of a object identification and tracking. So, micro robotics integrated with vision system combined with a microsensor can identify and track specific objects on a conveyor belt or in a space, facilitating precise manipulation or sorting. In addition to this, when we have a camera integrated micro robotics, so it can be used for several biological related applications. In fact, it can be used for some kind of an endoscopy related applications, etc., are some of the key domains which will be opened up when we try to introduce an object identification and tracking system along with the micro robotic related systems. Then we have a kind of a surface mapping. So, as far as surface mapping is concerned, though the micro sensors are integrated into a robotic arm, can provide a detailed surface topography information, allowing for precise path planning and adaptation to uneven terrains. Sometimes this can be efficiently used for kind of like mapping the overall surface roughness or manipulating the surface roughness based on the requirement or based on the characteristics. Now, let us discuss about micro transducer. So, as far as this micro transducer is a device that converts one form of energy into another at a micro scale. So, it plays a crucial role in microsensors by transforming the detected signal into a readable output. Such small device can be used for variety of purposes, including the medical imaging, acoustic mapping and biosensing. Especially when we try to talk about these kind of transducers, when we are working on the micro transducers level, several challenges are observed. Some of the key challenges includes signal conditioning, and the other challenge includes the energy requirements of the system. So, and the third challenge is impact of the environment towards these systems. So, these are some of the key challenges which basically micro transducers used to face. So, now, when we try to classify these micro transducers, so the micro transducers for robotic application can be considered under five main category. One is a kind of a pressure transducer, second is a kind of a piezoelectric transducer, third is a kind of a capacitive transducer, an inductive transducer and an ultrasonic transducer. So, let us discuss about the different types of transducers which are used for micro robotic applications in detail in the upcoming classes.